This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. DigitalOcean stands out from the crowd due to its simplicity, high performance, and no billing surprises. Join a community of over 3.5 million developers on DigitalOcean. Sign up with a free credit at do.co/SERadio.
For Software Engineering Radio, this is Robert Blumen. Today, I have with me Chris Richardson. Chris is an experienced software architect and consultant active in the field of microservices. His startup, Eventuate.io, provides a platform for the development of transactional microservices. Chris is the publisher of the website Microservices.io and the author of the recently published book, Microservice Patterns, which we will be talking about today. Chris, welcome to Software Engineering Radio.
Well, thanks. I'm pleased to be here.
Chris, would you like to tell the listeners anything about yourself that I didn't cover in the bio?
Well, I think you just about covered it. I mean, these days, as well as working on my startup, I basically travel the world helping clients adopt microservices through a combination of consulting and training.
Let's get on to Microservice Patterns. We have done a number of other shows on microservices, including number 213, 210 on architecture and microservices, and 351 on orchestrating microservices. So we're not going to do an in-depth review, but tell the listeners, what does microservices mean to you?
So today, like software technology or the ability to deliver software rapidly, frequently, and reliably is becoming essential to most, if not all, organizations, right? The whole concept of software is eating the world. And so in order to deliver software rapidly, frequently, and reliably, you need a combination of, should we say, three things. First is you need to embrace DevOps, right? A set of practices, essentially a software development methodology. You need to structure your engineering organization into small autonomous teams, so-called two-pizza teams, although that's somewhat of an imprecise metric. And then lastly, you need an architecture that supports all of this. And on the one hand, if you're building relatively small applications, you can probably get away with using the monolithic architecture. But if you've got a large number of developers and you're building a large complex application, chances are you actually need to use the microservice architecture. And essentially the microservice architecture breaks up what would otherwise be a monolith into a set of relatively small but not tiny services that can individually be developed and tested and deployed and scaled by the team that owns them.
I want to move on now and talk about design patterns or microservice patterns. When the book Design Patterns came out some 20 years ago, I believe the authors did not see themselves as really originating these ideas. They were more documenting solutions to problems that had been discovered and proven themselves over time. With your work on microservice patterns, what is your assessment of the state of the community in terms of adoption? Is there an agreed upon set of best practices, or is this more your view of how things should be done?
I would say my book is kind of a combination of both. I mean, you're right. I mean, in many ways, there's no such thing as a new pattern. It's really a kind of essentially a labeling and a more formal description of something that has existed within whatever field you're studying for some period of time, and it has demonstrated itself to be generally useful. So so a lot of identifying patterns is really just mining what people are doing, perhaps in some cases giving them a name, and then kind of trying to distill down a description of the solution, but then also describe the benefits and the drawbacks of that particular approach. So it's sort of a way of structuring something that has existed out there already.
Would it be fair to say then these patterns become a toolbox for architects to build their own microservice-based architecture?
Yeah, I think that's a good way of thinking about it. I mean, one of the key ideas with patterns in general, and sort of my book in particular, is that when you apply a pattern, right, and the pattern, the definition of a pattern is a reusable solution to a problem. You apply a pattern that actually solves some problem. In the case of the microservice architecture, the problem you're trying to solve is, how do I structure my application in a way that requires rapid, reliable, and frequent delivery of software? But at the same time, that actually invariably creates sub-problems. For instance, with a microservice architecture, one obvious sub-problem is, well, how do you break up your system into a set of services? And then there's also a whole bunch of patterns related to, well, you're now building a distributed system, and so there's some various problems around that. And so it's essentially you apply one pattern that creates sub-problems, which you then apply other patterns to solve. And effectively, you're sort of, you're doing that recursively, so to speak. And so these patterns form a web of interrelated patterns. And so when you are creating an architecture, you're essentially traversing this graph, selecting patterns, and then selecting patterns to the sub-problems, and so on and so forth. So it actually kind of provides a structure to this problem space, and tells architects what problems they're going to encounter, and then also how to solve them.
Given that design patterns, they are the solution to a problem, what are some of the problems posed by microservices that you don't have with the monolith that require a new and different set of patterns to solve?
Yeah. So first problem is, what services am I going to have? It's like, that's the key question. It's not, which deployment technology are we going to have? Should we use serverless versus Docker or anything like that? In reality, a lot of those technical issues that people tend to focus on are much more like a detail. So number one is, what services are you going to have? And then and there's some patterns for that. And then once you've come up with a set of services, it's like, one key aspect of the microservice architecture is that each service's data is encapsulated within that service. And that immediately creates two sub-problems. How do you implement transactions that span services? And then how do you implement queries that span services? And so that then leads to the Saga pattern, which is a way of managing transactions. And then there's a couple of querying patterns, API composition and CQRS, that solve the querying part of it. So that's sort of like, there's sort of, if you think of it as it's kind of a graph or a tree, that's one major sort of sub-branch of pattern solution, problem solution pairs that you end up going down.
summarize, you're drawing attention to going from centralized data to distributed data, possibly multiple data stores, as introducing a whole set of problems that the architect has to solve. Is that correct?
Yeah.
Okay, great. Just wanted to summarize that.
I would say a point of clarification is, on the one hand, services might actually have, in a very literal sense, their own database server. But quite often, all you need is sort of kind of a logical separation of data. So like you could have a shared relational database server, and then on that server, each service can have its own database schema. So logical division. Now, obviously, it all depends on the scale and scale and complexity of your application. But I don't want anyone who's listening to go, oh my God, I have to buy 10x as many name your database vendor licenses in order to do microservices.
What I think you're talking about is in a monolithic application, there could be one single schema. And if it's in a relational database, I'm free to write a query that joins the user table to the orders table to the product table to the product description table. There's no limit on how big of a SQL join I can write as long as it will run. But in microservices, at minimum, you might have user, orders, product in their own microservice, and they might still all be on the same server, but you're not going to allow SQL to join across those boundaries because they're, at minimum, it's a logical boundary. Is that where you're going with that point?
Yeah, that's exactly right. The tables of a service are essentially equivalent to the private fields of a class. It's part of its implementation, and they are hidden from the outside world, and they're only accessible indirectly through that service's API.
Great. So we've been talking about a set of problems that are caused by going from more of a distributed or partitioned data model. I believe you had another set of problems in your graph of problems that you were going to highlight that are specific to the microservice architecture.
Oh, yeah. So another sort of class of technical problems are, well, I've got a bunch of services, and then how do they communicate? Now, on the one hand, inter-process communication is sort of happens in a monolithic system because a monolithic application has to communicate with other applications, but I would argue that the degree of complexity around that is significantly higher in a microservice architecture because the services that make up the application are having to communicate with one another. So it's sort of inter-process communication is much more central to your application architecture. And so there's sort of basic patterns like, should you use asynchronous messaging versus synchronous communication mechanisms such as REST or gRPC. So that's sort of one sort of sub-problem that you have to address.
So let's move on to talking about what some of the patterns are. And since we're talking about communication, you do introduce these different families of communication patterns between microservices, synchronous and asynchronous. Could you break down when do you choose one, when do you choose the other, and what are the strengths and weaknesses?
Yeah. So on the one hand, let's just say using REST is in a sense the de facto communication mechanism, right? JSON, or to be more precise, JSON over HTTP. That's super familiar. Everyone, it obviously works with browsers, but then it's just super familiar. So on the one hand, that is kind of simple to use, but on the other hand, that actually introduces tight runtime coupling between the services. If say the order service implements a REST API, and then it while handling one of those requests, it has to make a synchronous call to the customer service and wait for a response to come back. Then in that situation, there's temporal coupling between the two. The order service can't send back a response unless the customer service can send back a response. And suddenly the availability of that endpoint is the availability of one service to the power two. And if you end up with more complex architectures and more complex patterns of interaction, the availability of your system or of your API starts to drop off dramatically. And so for those reasons, it's actually preferable to rely on asynchronous communication as much as possible. And in fact, a common anti-pattern is to go, well, we're just going to break our system up into a bunch of services and they're going to communicate using HTTP, right, or REST. And there you've basically built a system that's tightly coupled at runtime with multiple points of failure.
In your book, you introduce a recurring example of the food to go software as a service. Could you briefly describe that example and talk about a couple of points in food to go that would use synchronous and another one or two that would use asynchronous, and why you choose one or the other?
Oh, yeah. So it's an online food delivery application, along the lines of Uber Eats or DoorDash or Deliveroo. And, my first book, Pojo's in Action, which came out 13 years ago, had the same example, but it was a monolith. So the scenario envisaged in Microservices Patterns is, 10 plus years have gone by, and the food to go application has outgrown its monstrous, it now has a monstrous monolith and is having problems delivering software rapidly.
I'm sure we can all relate to that.
It's an incredibly common scenario, right? So in the case of the microservice version of that application, we take a request like placing an order. Several things have to happen when an order is placed. You have to do some validation around, can the consumer place orders? Is the order valid from the restaurant's perspective? Is the restaurant's kitchen willing to accept orders at this time? And then you also have to charge the consumer's credit card as well. So in the monolithic application, conceptually, all those happen inside the monolith. But in the microservice architecture, the order service ends up collaborating asynchronously with numerous services, such as the consumer service, the kitchen service, and the accounting service. And it's also subscribing to a stream of events that are coming out of the restaurant service so that it has a replica of the restaurant's data in its own database, so it doesn't actually have to interact with the restaurant service.
I'm going to not go through every single one of those, but I'm going to pick one. Why would the collaboration with the accounting service be asynchronous?
Well, one way to think about it is sort of the model is, so there's a REST, so the order service has a REST API to create an order. That API actually returns immediately essentially saying the request to create this order has been received. Check back later to see what the status of it is. And all of the processing required to basically validate and finalize that order happens asynchronously, including charging the consumer's credit card. Now, in the normal case, that everything should happen within, let's just say, tens of milliseconds, well, maybe within a couple of hundred milliseconds or something like that. So from the user's perspective, the order could actually be processed instantaneously. But the nice thing is where one part of the system is temporarily down, orders will still be accepted, just that the processing of them might be delayed briefly.
What you're driving at then is the decisions you make about what's synchronous and what's asynchronous will have an impact on the availability of the system and its ability to do work and accept business requests from the customers.
Mm-hmm. Yeah, you end up with sort of asynchronous communication. The general availability of the system is higher. It can still, in this example, accept requests to create orders, even if part of the system is temporarily unavailable.
I can see how from this conversation, when you talk about one thing, it's hard to completely separate that from everything else. And while we're talking about communication between microservices, you're introducing issues around transactionality. And I do want to now explicitly move on and talk about transactionality and how it's different in microservice application. You mentioned the Saga pattern. What problem does the Saga pattern solve, and how does it solve that?
So basically, the Saga pattern is a way of implementing transactions that span services. So within a service, you have, traditional, assuming you're using a relational database, you have traditional ACID transactions. But between databases, it's sort of, you could say that using ACID transactions in the form of two-phase commit or XA has fallen out of fashion for a variety of reasons, including that two-phase commit is a form of synchronous communication, which, as mentioned earlier, impacts the availability of your system. So the idea with Sagas is that instead of having a transaction that spans multiple services, a two-phase two PC transaction that spans multiple services, you break it down into a series of local transactions in each one of the services that contains data that needs to be updated. So in the case, if we simple example that I use is, imagine like in order to create an order, you have to check and reduce the customer's available credit. Imagine like there's a business rule that says the customer's customer has a credit limit that can never be violated. So in this example, you need to create an order and reduce the available credit. So those are updates that need to happen in both services. And so the way that's done with a Saga is, you could, for instance, you create an order in one service, in the order service in the pending state. That then sends a message to the customer service to reserve credit. And then the customer service sends back a message to the order service saying that credit was approved, was reserved, or maybe there was insufficient credit. And then the order service can approve or reject that order. So you've broken it down into a set of steps that are local, with messaging as the coordination mechanism between them. And so that's sort of an event. Essentially, that is an eventually consistent model for transactions.
If we were in a monolith, I could do some code, and it might not look exactly like this if you read the code, because you have all this propagation of transactions through different layers, but we're still in the same process. So I could do begin transaction, save the user, debit the credit, insert the order, insert the charge information, insert delivery address, and commit. And it's,
yep.
If everything goes well, it's all going to be saved. The worst case is it wasn't saved, but we don't have this problem of we debited the credit and we inserted the delivery address, but no order was created. It's, at least we can say it's all or nothing. Now, in the microservice world, you're talking about these things being in different services, and some might fail, some might succeed, and you're solving that with the Saga pattern. It seems to me for this to work, you need to ensure that when you commit something, that you've committed the message atomically along with the work that each microservice has done locally, and that you're sure that the message will get delivered. Am I correct in going that direction?
Yeah, it's funny. We're like getting deeper into this graph of problem solutions, right? we've gone from the microservice architecture to the database per service pattern to the Saga pattern. And now we're in this what kind of sub-problem area, which I call transactional messaging. And interestingly, so yeah, as you identify, there's each step of the Saga needs to do two things. First, it needs to update the database, create an order, or update the customer's credit. And then it needs to send a message to say that it's done that. And ironically, in a traditional application, you might use a distributed transaction for that spanned the database and your message broker. But that's essentially the kind of technology that we're trying to avoid. And so in order to atomically update the database and publish a message, there's two patterns that you can use. So one pattern is the transactional outbox pattern. So this pattern, as part of the ACID transaction that updates the database, it inserts a message into an outbox table. So that's just done atomically, right? And then there's a second step that is retrieving the message from that outbox table and publishing it to the message broker. And that will give you the atomicity that you need, along with the guarantee that eventually that message will be published to the message broker.
And the message broker is some technology like Kafka or RabbitMQ or something that handles the delivery of messages between the services.
Correct. Yeah. So the message broker needs to provide certain guarantees. It needs to give you at least once delivery. It also needs to guarantee or give you ordered delivery. These sort of these messages or events need to arrive in the order in which they were published. Otherwise, things could get really confusing. And so there are certain, and there's another problem where you need to somehow scale up consumers while also guaranteeing delivery. And so message brokers that provide all three out of the box include Kafka and ActiveMQ. And then to scale out the consumers with a couple of other brokers, it was RabbitMQ and also Redis Stream specifically. The open source project that I work on, Eventuate, as you mentioned, eventuate.io, we ended up building some extra code on top of those message brokers to enable scaling out consumers properly.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can develop faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity, high performance, and no billing surprises. Try DigitalOcean for free at do.co/SERadio.
We have a show coming up on messaging architectures, which it doesn't have a show number yet because it hasn't been published, but it will be published by the time people are listening to this, and it will go into some of these issues. In interest of time, we won't by any means be able to cover even all the major areas in your book, but I wanted to hit on some of the stuff that I thought was the most interesting. I wanted to move on to another area, which is introduced near the beginning of querying. You introduced the pattern of the API gateway. What is that pattern and what problem does it solve?
So the API gateway is one of the communication patterns, and the area that it's focused on is what I call external API. So in other words, what API does the application expose to the outside, which might be literally the outside of the firewall, or it could just be other parts of the organization.
If I have 100 microservices, they may not all be public.
Correct. So the idea with the API gateway is that it's similar to the facade pattern in object-oriented design. It defines the public interface of your application. So clients talk to the API gateway, and then it's responsible for implementing each, say, REST endpoint by invoking the appropriate services. It generally does three things. One, it will just simply function as a reverse proxy. So routing each incoming request, like create an order, it will route that to the order service. It will also implement edge functions such as security, potentially other things like rate limiting and so on. And then it might also implement API composition. So imagine that a client wants to know the status of an order. So that order status could actually be scattered across multiple services. So the order service would know some parts of the order status. The kitchen service would, in the food to go application, would know about the status of the order at the kitchen. Like, when is it in the middle of being prepared? Is it, what's the estimated ready for pickup time? And then the delivery service will know about the estimated delivery time. And then perhaps if it's in the process of being delivered, where it is. And then, say, the accounting service would know other things. So it's like the status is scattered across, in that example, 4 different services. So rather than the client making 4 different requests, it just says to the API gateway, give me the order status, and then the API gateway goes and makes requests to each of those services, gathers back the 4 responses, and returns the response to the client. And that has 2 benefits. One is a sort of performance or efficiency aspect, particularly if it's like a mobile device making a request over a lower performance, higher latency mobile network. But it also it basically is encapsulating the internals of the architecture. So the clients are not aware of the individual services, which is a good thing because the architecture can evolve.
I think one of the things you're talking about in this case is an issue you identify in the book by the name Chattiness.
Yes.
Go into more. What is Chattiness?
So essentially, there ends up being there's often a mismatch in granularity between the data that the client wants to render on a page or a screen, and the fine-grained nature or relatively fine-grained nature of your services. So in other words, especially with a desktop user experience, you think about like the Amazon product detail page, it's displaying a heck of a lot of information. Basic product information, delivery estimates, when you last ordered it, perhaps, whole bunch of reviews, 2 or 3 different kinds of recommendations, seller rankings, so on and so forth, right? You could imagine that each of those individual pieces of data resides in a service. And so one page can easily correspond to potentially tens or more services. And so if the client had to get each one of those pieces of data individually, that results in a lot of round trips, which for certain types of clients, especially mobile devices, would be generally not a good idea, right? It's potentially poor user experience. There's the risk of draining the battery faster and so on. So the idea is with the API gateway pattern is that each client can be given its own optimized API, which in some cases, applications I've worked on, it's almost like for each screen there is a dedicated API endpoint that so the client can just give me the data, and it gets back a blob, relatively large blob of data that's basically joined from or composed by calling multiple services.
So in the monolith, you would do a lot of this integration in SQL where you'd hit an endpoint and it would go and join a bunch of tables together. It sounds like what you're doing here is you're moving that joining function into this API gateway, and you put the long haul hop in front of that, and then it's going out in the data center and doing super short hops to pull all these chunks together and merge them.
Yeah, that's essentially right. And so, one place to do that is in the API gateway, or the API gateway routes to a service that implements this composition.
Another issue you bring up is consistency, which you don't have in the monolith because you're always doing commits and leaving the database in a nice consistent state. Do you have a problem where this API gateway is going and hitting all these services and it gets back things that don't all quite make sense together because they reflect things that are in different states of convergence toward a consistency?
Yeah. So essentially, in a monolith, you retrieve data. You're most likely going to do that within a transaction that will give you a transactionally consistent view of the data. Whereas in a microservice architecture with API composition, multiple transactions, one in each service, are being executed. And so you theoretically could get sort of an inconsistent view of the data.
Is there a solution to that, or is that a trade-off that you need to make to get these other benefits?
I mean, fundamentally, that's a consequence of having split the system up in the way that you have chosen to split it up. I mean, one of the interesting things is, say, for a given set of requirements, there are potentially multiple different ways of decomposing the system. So, for instance, in this class, I teach this 3-day class where students come up with a microservice architecture for given a set of requirements. I think that typically the class will come up with 3 or 4 different architectures, and each one represents a sort of different set of trade-offs, in the sense that some queries might correspond to a single service, but other queries will require gathering data from multiple services. And then that's in architecture A. In version B, it's different. It's divided up differently, and which impacts different queries. And so essentially, if you find that because of the way that you've divided up your system into services, it results in a query that gives you unacceptable inconsistencies, you might actually have to go back and revisit your decomposition and adjust the service boundaries so that you have the consistency that you need.
We did a show a little while back about the PostgreSQL query planner. One of the takeaways from that show is the query planner is brilliant at costing out different ways of getting information and doing something that's pretty smart to get you all the information you want. And if you didn't have that, you'd be looking at, okay, I'll grab all the users and then I'll go out and get all these addresses one at a time. And you probably would do a worse job in the query planner. Are we taking a step backwards here when we decompose and now we are telling our developers to become essentially a SQL query optimizer, but maybe they're not as good at it as the one in Postgres?
I see the analogy there, right? In the sense that I think basically it sounds like you just write some giant SQL query, hand it over to the query planner, and it figures it out as opposed to breaking it up. I wouldn't say it's exactly the same problem, but there's a certain there are some analogies here in the sense that essentially things like transaction management, joins, maintaining referential integrity ends up being moved from the database, where it's just all automatic and you don't think too hard about it, up to the application level. So if you're using the Saga pattern, some aspects of what you're doing are more complicated, and then querying is more complicated. And then say foreign key constraints, you're now having to enforce those at the application level. So like when you create an order and it's got a customer ID, that's in the order service, and you can't have a foreign key constraint to the customer table anymore. So there's a bunch of stuff that you have to do at the application level, which makes things harder, right? But on the other hand, the assumption is that there are benefits to splitting up, right? And hopefully the benefits outweigh the drawbacks. So as it, for instance, if you're working on a service, hopefully the focus of your attention is on implementing, say, the complex business logic within the service, and the sort of the complicated stuff around sagas and querying are a relatively small part of what you have to worry about. Even though, like, my whole book is, you could say, it's on all this complicated stuff, but it's just that the idea, hopefully the complicated stuff is sort of on the periphery of your services, and the meaty stuff that's implementing the business logic is actually the bulk of what you're having to do.
Fair enough. I want to move on and ensure we cover as much as we can. One of the areas which is, in my experience, extraordinarily more complicated when you go to microservices is testing. What are the major differences in testing? And I'll say we've had a ton of shows on testing, almost all about testing program logic. What are the main differences from single program testing to microservice testing?
Testing in a microservice architecture is simultaneously, I would argue, easier, and it's harder. So it's easier in the sense that a service is a relatively small amount of code. And so writing automated tests for it are a lot simpler, and they're simpler and faster running than they would be if you had some monstrous monolithic application. So there is this notion that testability is enhanced by the microservice architecture. The complication comes from the fact that services often don't exist in isolation, right? Let's just say the order service is having to collaborate with the customer service. So there's a coupling there. Say the order service is dependent upon the API of the customer service. Whether that API is literally a REST API, or perhaps it's an asynchronous kind of API, there's still a dependency there. And so there's sort of a bunch of problems around that. Like, well, I want to test my order service, but it depends on the customer service. And then shall we say the customer service might depend on 3 other services. And suddenly you've got this whole tree of transitive dependencies just because you want to test one service. And that could actually get quite complicated quite quickly, because in theory, you're having to provision all of these services. So one important trick there is you want a way to test services in isolation while being confident that when you put them together, they can actually communicate successfully. So there's a few different patterns there. One key idea is consumer-driven contract testing, where the interaction between a consumer, a client, and a service is captured by a set of contracts, which are basically, in the case of HTTP, example request response pairs. So it's like specification by example. And those examples or contracts are used to test both the service and the consumer in isolation, and so if you're testing both with the same contracts, then in theory, fingers crossed, when you put them together, they can communicate. And then the other part of it is there's component testing for services, which is where you test a service in isolation, but you use test doubles for any of its dependencies. So the order service, for instance, would be tested in isolation with a test double for the customer service. And the test double would, if it was HTTP, would be programmed to reply with canned HTTP responses for a given, when it gets a request. Or if they're communicating via a message broker, it would be send back pre-canned reply messages. So there's a bunch of these newer testing techniques that you have to use, but the end result is you're able to test services in isolation while being confident that when you deploy them, they will actually communicate.
This sounds very much like the use of mocking, which I'm familiar with in Java or Groovy. You have a library which will instantiate at runtime a class that implements an interface, but you can script out what you want the methods on that class to do when you call them just for that test. And that could include returning a certain result or raising an exception. So you've abstracted that concept and moved it out to the HTTP server rather than the programming language. Is that correct?
Yeah. So like what you're describing, like with mock objects, like say with the Mockito framework in Java, that's a particular form of test double. But you can have other forms, such as a fake HTTP server. And then, for instance, there's the WireMock project that is an open source project. It's basically it's Mockito for HTTP. So that's pretty useful. And there's other ones like that as well. And then you can do the same thing with messaging as well. So if you've got services that are communicating via a message broker, it's pretty straightforward to have a test double that when it receives message X, it sends back message Y.
When you were talking about using these contracts, my first thought was I am going to implement an HTTP endpoint, and I think the variable in the JSON document has one name, but the client has a different idea of what the name of that field is. I think you've solved that by forcing both ends of the endpoint to use the same contract, and that should detect a lot of bugs that you might find at compile time if you were compiling your whole thing into one big monolith.
Yeah. I mean, it's very true that, especially when you're using a statically typed language like Java, any interface mismatches manifest themselves as compile time errors, which is really good, right? But in a distributed system, you don't have that kind of guarantee. Especially, well, the other key point is your system is not static. Services are constantly being updated, and so preventing APIs from accidentally being made, like introducing breaking changes accidentally in your APIs, it's really critical that you prevent that from happening. And so consumer-driven contract testing does exactly that. It prevents the service team from accidentally changing the API in a way that would break any of the consumers.
We did a show a little while ago about Jenkins. We had some fairly general discussions about the concept of a pipeline. Jenkins can execute any kind of pipeline. You have some views in your book about what the deployment pipeline would look like in a microservice architecture. Talk about that. What is the pipeline that you recommend?
So in general, I mean, a deployment pipeline is essentially a series of automated test suites. And the idea is as you go from left to right, the test suites potentially get slower and, well, more sophisticated and slower, but get more production-like. So maybe the first stage of your deployment pipeline might just execute unit tests. So they execute blindingly fast, but essentially don't catch a whole class of errors. And so then you have the next phase executes more sophisticated yet more expensive kinds of tests. And so a key idea there is that, yeah, you can go implement the deployment pipeline pick your favorite CI server or cloud provider. It doesn't really matter too much which one you do, but the important idea is that essentially each service has its own deployment pipeline. So it's being built and tested independently of all of the other services. And then, I suppose I should say, ideally, the final stage of the deployment pipeline actually pushes that service into production. I mean, in theory, it could all of these different per service deployment pipelines could feed into some kind of end-to-end testing environment, like what you would commonly call a staging environment. But, there's a lot of thinking around that, is that instead of having a staging environment, which is only a rough approximation of production, and also the fact that end-to-end tests tend to be kind of slow and kind of brittle, perhaps it can be much more effective to just deploy into production in a very disciplined way using like canary deployments or blue-green deployments, and with careful monitoring so that if there are problems, you can quickly roll back.
Moving on to another area you provide patterns is productionizing or production readiness. How do you define production readiness?
Well, there's all this, what should we say, there's one absolutely key part of what a service does is is the business logic, right? I mean, that's like the whole reason for it existing. But then in order to be sort of deployable in a real application, there's a whole bunch of other stuff that you have to deal with. For instance, security. That's obviously one really critical thing, right? Is services need to be secure. So that's one part of being production ready that's separate from the business logic. And then another big part there is observability. In a sense, well, you always have to deal with sort of observability or monitorability even inside a monolith, except that it's a bit more complex in a microservice architecture, because when requests come in, they can bounce around between services, and so troubleshooting and like figuring out where the latency is being is high is much more complex. In a monolith, I suppose you just you run a profiler of some kind and you can track it down. But if requests are bouncing around between a whole bunch of services, it's not so obvious. And so there's a whole bunch of observability patterns that you have to implement, ranging from simple ones like having a health check endpoint that the runtime environment can periodically ping, like make a HTTP GET request to verify that your service instance is healthy and and can handle production traffic. There's another pattern is log aggregation. So the logs from all of the services are being sucked up into a log aggregator where they're stored and they can be searched. Another critical pattern is distributed tracing. So, each inbound request gets a request ID, or a trace ID as it's called, that gets propagated from one service to the next, ends up in log messages, and then that interacts nicely with log aggregation, because then you can search for that request ID and see all of the relevant logs. Plus, the services report what they're doing to a distributed tracing server like OpenZipkin, which can then display traces. And you can get the time breakdown for a sample of requests, and you can see where the latency is being spent, it is occurring, and so on. And then there's other patterns like application metrics, right? Gathering metrics at the app or the sort of business level metrics about what your services are doing, and then feeding them into a metrics database where they can be aggregated, visualized, and alerted.
One that you didn't mention that I was going to ask you about is the externalized configuration pattern.
Oh, yeah.
Talk about that one.
So the basic idea with that, which is really one that's you'd have to deal with in a monolithic application as well, is the application should just be built once, right? Well, by the first stage of the deployment pipeline, and then you can run it in multiple environments. But what that means is that, say, the configuration properties of external services like the database server can't be hardwired into the source code because they're different in each environment. And so they need to be passed in at runtime somehow. And so you need an externalized configuration mechanism for doing that, which might be something as simple as setting environment variables. That works quite nicely in a Docker environment where it's easy to, whether you, like say if you're using Kubernetes, right, you have a config map that defines some property values that then get injected into the container as environment variables. And then, like if you're using Spring Boot will just pick them up and make them available inside the Spring application context. But there's other mechanisms that you can use, well, config files that get injected in, or you can have, so those are sort of the push model, or there's the pull model where the service can go and request its configuration from a config server. I mean, so you've got a couple of different options there.
What all these things, what ties them together that we've been discussing these last few minutes is enable you to manage, understand, and troubleshoot the application when you run it in the production environment. Is that a fair summary?
Yeah. Well, yeah, I suppose manage as in configure it and figure out what the heck it's doing.
Okay. We're getting pretty close to the end of our time. I had a section of questions about anti-patterns. Maybe I'll ask you, what is one of the most pernicious or most common anti-patterns that you observe?
Well, I would say there's two. I mean, so one is technical, which is where you create an architecture where you have a set of services that are communicating via HTTP, and perhaps with the assumption that networking is free. So you've taken a monolithic design, modularized it, and then given each module a REST API. So there you're likely to have performance problems because there's lots of network round trips. So latency will be horrible. Also, you've basically built a tightly coupled system with multiple points of failure. And then if you've really done a bad job of modularization, you basically end up with building a distributed monolith where changes to one service just ripple throughout the sort of all the chain of dependencies, and you end up having to make multiple changes to multiple services in lockstep. So you've basically got a monolith that's made of services, which is like the worst of both worlds. So there's sort of technical anti-patterns like that, but then maybe the more challenging ones are more sort of organizational, political, process, policy oriented, which I gave it a keynote, gave this talk, potholes in the road from monolithic hell, at a conference. And that, an example of those, one of them is called the red flag law. And its name comes from the fact that when automobiles or self-driving vehicles first came out in sort of the early 19th century, that some jurisdictions passed a law where a pedestrian had to walk in front of the car holding a red flag. So you kind of had, presumably the vehicle could actually go faster than the pedestrian, right? But you slowed it down because of the law. And I've seen this inside some organizations where it's like, yeah, we're going to have microservices, but then they don't change their policies or their processes, right? So, for instance, they might just stick with manual testing. Like automated, like many organizations, one of the biggest weaknesses is actually the lack of automated testing. So you've got this architecture that gives you the potential to deliver software really quickly, but then you basically have someone walking in front of it with a red flag, but because you've got manual testing, or maybe you've got policies that say no deployments during business hours and you can only deploy on the 4th Saturday of each month at midnight. So it's sort of like, you know, in a sense, you're missing the point of the microservice architecture, and you're not going to properly benefit from it.
Thank you for that. And we're getting pretty close to the end. Just to wrap up, we mentioned your company, Eventuate.io, Microservice.io, which has many patterns. Your book, where can listeners find your book?
Oh, yeah. So if you go to microservices.io/book, you'll find a description of the book and links to where you can buy it.
Do you have any upcoming conference talks that listeners might want to attend?
In September, I will, the full conference season, I'll be at some conference or the other.
Okay. Well, Chris, thank you very much for speaking to Software Engineering Radio.
Great. Thank you.
This has been Robert Blumen. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.